Okay, so I wanted to finish up with this like dissolves like concept. You'll find this on pages 153 and 154 of the guided notes. All right, so what we were saying is that in order for something to dissolve, the solute particles have to have similar stickiness or affinity for the solvent particles as they do for themselves. All right, the analogy that we were giving is like you and your friends at a party. All right, if you and your friends don't know anybody out there, you tend to stick to yourselves. But if you're friends with people out there, you're okay being separated from your group of friends. All right, same thing with solute particles. If it's a solid like a sugar cube, we know that these molecules have stickiness with themselves. All right, so why would they allow themselves to be surrounded by separated from their neighbors and surrounded by water molecules? There has to be some level of stickiness. All right. So the two examples that we gave in class were salt and water. All right. Remember the nature of salt. All right. It's an ionic compound, so a crystal of salt would consist of alternating positively and negatively charged ions. Why would these guys allow themselves to be separated if you put them in water? All right, so you have to remember that little property of water. It is a polar covalent compound, which means one side of it is going to have a slightly negative charge and the other side of the water is going to have a slightly positive charge. All right, again, that's due to the electronegativity of the atoms. And so if these ions were separated, notice that this positive ion could allow itself to get surrounded by the water so that the slightly negatively charged side of the oxygen was facing that positively charged ion. All right. In contrast, the negatively charged chloride ion could allow itself to get surrounded with the slightly positively charged hydrogens of the water facing it. All right. So there is an attraction between the solvent particles, the water molecules, and what the atoms that the solute is made of. All right. In contrast, if you took that same grain of salt and you put it in gasoline, well, the big difference there is that gasoline is a nonpolar covalent compound. All right. There aren't any delta positives, delta negatives that you could draw on the atoms of a gasoline molecule in the same way that you could a water molecule. So if you drop this crystal of salt into gasoline, essentially these ions have a much stronger attraction for themselves than they do for these gasoline molecules. Therefore, they would rather stay stuck to each other than be willing to separate. That means that they're going to remain undissolved. All right. So, a couple of new examples. Let's consider what happens when you put sugar in water. Okay, this molecule right here, I'm kind of circling it. That would be a sugar molecule. So if you have, actually technically this is glucose. Table sugar is called sucrose, which is very similar to this. But essentially, if you had a pure sample of this compound right here, it would be a solid. All right. Why is it a solid? Because it's got all these OH bonds in it. And if you remember from talking about hydrogen bonding, whenever you have OH bonds in a molecule, they like to stick to each other because they can perform hydrogen bonding. All right. So what happens when you put sugar in water? All right. Well, you'll notice I've drawn a lot of water molecules around this sugar molecule. And you'll notice, all right, right here, we can have an oxygen right next to the hydrogen of that water. All right, that would satisfy the requirements of a hydrogen bond. All right, here's another water molecule. That would be a hydrogen bond. Here's another water molecule. Here's another water molecule. All these are hydrogen bonds. All right, so a sugar molecule would have a very sticky relationship if you surrounded it by water molecules. All right, and this is what allows sugar to be soluble in water. All right, let's contrast that to what would happen if you dropped sugar into gasoline. All right, this is the same molecule that we have here. I've just drawn it with a little bit of shorthand in it. All right, these are your gasoline molecules right here. It's made of nothing but carbon and hydrogen. And what you'll notice is that there's really nothing about this that would be sticky with these oxygen hydrogens. Okay, so again, this is a sugar molecule, and remember what holds the sugar molecules together. It's the hydrogen bonding, all right? So there's all these OH bonds in it, and whenever you have those in molecules, they're going to be very sticky for each other, all right? Well, do we see anything about a gasoline molecule that would be sticky with a molecule like this? All right, there are no delta positives, delta negatives in this, so the sugar molecules would have a much higher stickiness between for themselves than they would for any gasoline molecule. Therefore, all these guys would just rather stick together, and they would sink if you put it into a container full of gasoline. All right, but what about if we had wax and we put that into water? All right, so what is the nature? So we know that wax molecules stick to each other because it's solid. What is the predominant reason they do that? It would be the London dispersion forces. Again, we look at things about this molecule. Are there any polar bonds? No. Can it possibly hydrogen bond with a neighbor? No. All right, so that's the type of interaction that holds these guys together. Well, what holds water molecules together? It's going to be that hydrogen bonding. All right. So if you put this into water, would these guys rather stick to their neighbors, or would they rather stick to these water molecules? And there aren't any favorable interactions between a wax molecule and this water molecule. Therefore, these guys would prefer to stay stuck to themselves, and that little sliver of wax would just float on top of the water. All right. But let's contrast that to if we were to add some wax to gasoline. All right, so notice that the types of atoms and bonds that you have in gasoline are very similar to the types of atoms and bonds that you have in that wax molecule. All right, the very same force that allows these wax molecules to stick to each other is the same force that would exist between gasoline and that wax molecule. Therefore, a wax molecule is very happy to allow itself to get surrounded by all of these gasoline solvent molecules, and therefore if you drop that wax in the gasoline, it's going to dissolve very well. All right, so again, these phrases can be summed up in this phrase, these results can be summed up in this phrase, like dissolve like, which means that things like to dissolve in things that are similar to themselves. All right, so compounds with charged character, which means ionic or polar covalent compounds, tend to dissolve in each other, but not in things that don't have that charged character, nonpolar compounds. All right, this is an example of a nonpolar compound. There are no positive and negatively charged atoms. There's no delta positives or delta negatives on it either. All right, so alternately, nonpolar compounds tend to dissolve in each other, such as when wax would dissolve in gasoline. Some other things that you would expect to do this, something like mineral oil or baby oil would mix very well with gasoline. One way that you might see this being applied is if people are ever trying to clean up an old bicycle chain. All right, when a bicycle chain gets very full of dirt, there's a lot of grease in there, and if you've ever seen how that chain reacts in water, the grease doesn't, the water and the grease don't like to mix. How do you get that grease off of the bicycle chain? One thing that you can do is just put it in a little container with gasoline. The gasoline dissolves that nonpolar grease very well. All right, so I believe that's it for like dissolves like, and we will talk about some other subjects in a future video.